Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. In a previous video, I took a look at a voltage divider constructed with operational transconductance amplifiers instead of the usual resistors, which seems like a strange thing to do unless you're in the realm of MOSFETs on a chip, in which case MOSFETs are cheap and the resistors are more expensive, relatively speaking, in terms of real estate, complications, etc., etc. And I would suggest that you watch that video if you haven't already. Anyway, we have two OTAs that are playing the roles of resistors. I have their bias current set to be the same, so their transconductance gains are the same. So this is basically a divide by 2. Now, I'm referencing all of the voltages relative to 1.25 because my upper rail voltage is 2.5 volts, and that's how I'm going to display things. So when I run this particular simulation, we'll see that everything's centered around 0, although in the circuit, it's really centered around 1.25. Now, because OTAs are nonlinear devices, you'll see that they start to saturate at a particular point. But within a nice particular region, we get this gain of a half. Let's see. So if we look at this particular point here, say 0.5, we see we get 0.25. Similarly down here, if we're at minus 0.5, it's somewhere around minus 0.25. And beyond that, it sort of saturates and levels out. But this makes a lot of sense. Now, if we want to make the first number here bigger, let's say we change this number to 4, and we take a look at that, that will indeed simulate. And then we're getting something that's a lot closer to just a straight line. If we keep pushing that further, we get something that's closer and closer to a voltage follower. And that's basically what I showed last time. But let's flip this around. What if I made this 4 and I made this 2? So the gain of the first OTA is smaller than the gain of the second. Well, if I do that, then I wind up with this little flashing exclamation point here indicating that the Medelica simulator is unhappy. It turns out the solution to this, as suggested by one of Professor Jennifer Hassler's graduate students, is to add in a capacitor at the output of the OTA here. Or I should say the output of the OTAs, since the outputs are connected. So what I'm going to do is I'm going to pull up the palette browser and pull up the capacitor, which is actually built in. Let's see, so here's a capacitor. Let's drag that over here. I'm going to need a ground, so we'll copy a ground here. We'll put it here. Here's the capacitor. I'll put the negative terminal facing downwards towards the ground, and then we'll connect this up here. And Medelica is really bizarre about why did it put it there. I shouldn't say Medelica. I should say Excos is really awkward and weird. Why is it doing that? Okay, let me see if I can fake it out again. It's really very strange in terms of how it makes connections. Like, I really don't want it to connect there. Why can't it connect here? Okay, let's see if I... Well, why would it do that? Okay, one moment. I'm going to actually stop the recording and fight it for a bit. This is the thing you do. What you do is you fight the Excos routing mechanism. Okay, after a bit of fighting with Excos off camera, I finally got this nice leak. Anyway, what we want here is a capacitance that's very tiny. So I'm going to put e to the minus 15, and let's see if that will simulate. And see, this is another Excos bug. Why did it turn it sideways? I don't want it sideways like that. I want it like that. All right, so let's play this. Simulate this, I should say. Oh, and look at that. It did indeed simulate. So basically, it looks like under some circumstances, Medelica doesn't like parameters to change too quickly. Oh, look at that. Isn't that nice? And putting the load capacitance here at the output of the amplifiers makes Medelica happy about that. Let's see. Let's change this one here to 1 microamp, and we'll change this one to 9 microamps. So remember, this is proportional to conductance, not resistance, so you have to flip around your usual resistor divider formulas in your head a bit. So this should be giving me a gain of 1 over 10. All right, so let's simulate that. And we can then blow this up here. Let's see. And the way this is working, it's hitting the saturation at some point. So we can't really look at 0.1 and find 0.01 because it's already gone into saturation. Let's look more at what might be 0.05. So if we look at 0.05 a bit, let's see. Okay, that's more along the lines of, yeah, that's like 0.005. So within the linear range, we're seeing this gain of 1/10. If we're pushing past that, we're going into saturation. But this is operating the way we expect. Beautiful. So I found this capacitor trick to be incredibly helpful. Basically, all of the simulations that I've been trying for the past couple of weeks that I haven't shown you because they weren't working, I can now show you in future videos because this capacitor trick fixes the problem. Again, just a very tiny little capacitance here makes the simulator happy.